This is Chapter 4, Identifying Electron Configurations of Elements and Ions, Introductory Chemistry at Mineral Area College. So this is what's referred to as an electron configuration tree, which will help you guys remember the different electron configurations on the periodic table. Notice how the numbers keep on increasing and there are the same amount of numbers depending on the row it's in. So like for instance, row 1 would have 1 number, row 2 would have 2 numbers of 2, row 3 would have 3 numbers of 3, row 4 would have 4 numbers of 4. Right here is whenever the pattern sort of stops. And just remember that between row 4 and row 5, it's a reflection, so there's going to be 4 5s. Then there's going to be 3 6s, 2 7s, and then notice how there's not an 8s at the bottom to sort of complete like the triangle, simply because 8s does not exist. So now I will fill in the periodic table so then you guys can understand. So here we have the periodic table filled out with all of the S, the P's, D's, and the F's. And so this is the trick. You start with 1s. So 1s is going to go from hydrogen to helium. Then you just follow the arrow. It's going to be 2s. 2s is going to be from lithium to beryllium. Then once the arrow is finished, you go up to 2p. 2p is going to be from boron to neon. Down the arrow, 3s is just going to be from sodium to magnesium. Then you're finished with the arrow, so you go over to 3p. 3p is going to be from aluminum to argon. 4s is just going to be from potassium to calcium, and so on, so on, so on. You guys get the trick. But basically, we're not going to be dealing with the 4Fs or the 5Fs in Intro to Chem, so you don't have to worry about those. So now we're going to find the electron configuration of fluorine, the element. Now the atomic number is 9, so it is going to be right here. Okay. Now we know that to get to fluorine, we can pass 1s2 because S can hold up to 2 electrons. So 1s1, 1s2, which is helium. Then we know that X1 is going to be 2s. 2s is going to be from lithium to beryllium. So it's going to be 2s2. Then we know that after the 2s is going to be 2p according to our electron configuration tree. So 2p is going to be this row. And so we know that this is going to be 2p1, 2p2, 2p3, 2p4, 2p5. So fluorine is going to end at 2p5. And the noble gas core electron configuration of fluorine is going to be helium 2s2, 2p5. The reason why we can replace 1s2 with helium is simply because helium has the electron configuration of 1s2. So this rule is implying that helium is just the same thing as 1s2, which is true according to our electron configuration on the periodic table. Next, we're going to find the electron configuration of fluoride. Now notice how the ending is IDE, which is a different suffix. And so the IDE suffix tells us that it's an ion. And since it ends in IDE, it is an anion, so it's going to gain an electron. It's going to be more negative. Fluoride has an F and a -1 charge because it's going to gain 1 more electron to be close to neon. It's not going to lose a whole bunch of electrons to get to helium, but it's going to gain 1 electron to get closer to neon. So again, we start up with 1s2, then we finish 2s2. Now this part's going to be tricky. It's actually going to be, instead of 2p5, it's going to be 2p6 because remember, fluorine just gained one more electron. So if you're gaining one more electron, it's just the same thing as saying 5 plus 1. So in the 2p. So if it's 2p5 and it's gaining one more electron, then it's going to be 2p6, which makes sense because the electron configuration of 2p6 is the same thing as neon. Remember, this is 2p1, 2p2, 2p3, 2p4, 2p5. 2p6 is neon, and it makes sense that it ends in 2p6 because fluoride wants to be like a neon. It wants to have sort of like the same electron configuration whenever fluorine is in its ionic form, which is fluoride. So on to the next one. We have calcium, which is right here, has an atomic number of 20. So with our electron configuration tree, we're going to start off with 1s. And we know that s can hold up to 2. So we just finished with helium. So 1s2 is going to be helium. Then down to 2s. 2s is going to be right here between these two. We know that s can hold 2. So then next in our electron configuration tree, it's going to be 2p. 2p6 is going to end with neon because we know that p's can hold up to 6 electrons. Then down in our arrow is going to be 3s. 3s is going to be from sodium to magnesium, but we know that s can hold up to 2. So it's going to be 3s2. So we just got done with magnesium. Then we're going to go over to 3p. 3p is going to be from aluminum to argon. We know that p can hold up to 6, so it's going to be 3p6, ends in argon. Then we know that's going to be 4s, so potassium to calcium, and since s can hold up to 2, this is going to be 4s1 and 4s2, so calcium is going to end with 4s2. The electron configuration is going to, for the noble gas core, is going to be argon and then 4s2, because this entire thing right here, has the electron configuration for argon, because argon ends in 3p6, so we can substitute it for argon over here. So all we're left with is 4s2. Now for the ionic form, we know that calcium ion, it's going to be Ca plus 2 because calcium is going to lose 2 electrons. It's going to jump back to get closer to argon. Then it is going to jump a whole bunch just to get to krypton. It's going to take less energy to lose electrons to get to argon than to gain a whole bunch of electrons to get to krypton. So calcium is Ca plus 2. So we know that up to here, 3p6 is going to be krypton, and then we would normally, 3p6 is going to be argon, and then we normally know that calcium as an element is going to have 4s2. However, because it lost 2 electrons, we can say that 2 minus 2 is just going to be 0. So 4s0 is just not going to be there anymore, right? Because if we lose 2 electrons, since 2 minus 2 is 0, 4s2 is not going to be there anymore, and now it's going to be, its calcium ion is going to end in 3p6. And this makes sense because it wants to be a noble gas ideally, right? Because it's in its ionic form. And so 3p6 is just the same thing as argon, and so calcium ion is going to have the same electron configuration as argon, because then it wants to lose its electrons to turn into like a noble gas. Okay. My final example is going to be identifying the electron configuration of zinc. So zinc has the atomic number of 30, so it's simply going to be right here. So let's start off with our electron configuration tree. So we have 1s, so 1s2, 2s2, 2p6. So we just got done with neon, which is at 2p6. Then down our tree, we're going to go to 3s, which is from sodium to magnesium. We know the s fills up 2, so it's going to be 3s2. Then we're going to go over to 3p. 3p is going to be from aluminum to argon. 3p6 is the maximum for this row. Then we know it's going to go down to 4s. 4s is going to be from potassium to cesium. We know that s can hold up to 2, which is the maximum. Potassium 4s 1 is its electron configuration. And then calcium is going to have an electron configuration of 4s2, so that's where we're ending right there. And then according to our electron configuration tree, we're going over to 3D because we just finished the arrow. So 3D, we start with the D's over here. And so scandium is going to start us off with 3D1. And since copper is all the way over here, it's going to be 3D10. It's because 10 is going to be the maximum value for D. Now its noble gas core electron configuration is going to be AR 4s2 3d10. We can say that because we know that this entire thing over here is going to be the electron configuration for argon, right? Because argon ends right here. It ends at 3p6. And so we're going to continue the 4s2 also, which is all the way up to calcium, and then we're going to, leave the rest, which is all the way up to 3d10. Now, to find the ionic configuration, it's a little bit tricky. Because it is a transition metal, its electron configuration is going to be a little bit different this time than the previous example from the last slide. And so we're going to basically copy down everything, but notice how zinc ion has a positive 2 charge. Okay, so this is the electron configuration of zinc as an element, right? Because we just did it. Now, if zinc has a +2 charge, that means that it lost 2 electrons, right? Because if it loses 2 electrons, then it's going to be 2 more positive. Note that it does not mean that it's gaining protons, because if it gained protons, that would completely change the element, but gaining or losing electrons does not change the element itself. So zinc ion is a transition metal, and it doesn't follow one of our octet rules really, because since it is a transition metal, it kind of does whatever it wants to. But zinc normally has a positive 2 charge. But anyhow, if we lose 2 electrons, then we're going to subtract 2 from one of these numbers. Notice how we end in 3d10. You would normally think, oh, I'm going to subtract 2 from 3d10. However, you can't do that because theoretically 4s2 is the most outer shell of the atom, of the element. So now we're actually going to subtract 2 from the 2 and the 4s2. And that's because the numbers in front of these letters symbolize different energy levels, 1 being the closest to the center and 4 being the most outer of the center, right? It's going to be the most further out. And so if we lose 2 electrons, then we're going to lose the electrons on the energy level that is the most furthest out, because that's where our electrons are going to lie. So it's actually going to be subtracted from 4s2 instead of 3d10 for that reason. It's just simply because if this was going to be how we draw zinc, okay, pretend that these are the protons and neutrons inside. This is the first energy level, this is the second energy, the third energy, and fourth energy. Remember how on zinc there is a 4s2, so there's going to be 2 electrons on here? Well, if zinc ion is going to lose those 2 electrons, then the first electrons that are going to leave is going to be the electrons on the 4th energy level, indicated by the 4 and the 4s2, okay? It's not going to be from the 3d10 because 3, this is the 3rd energy level. And so obviously it's going to lose the one that's on the outermost. That's all I have. Thank you for watching.